This diagram in this slide shows AES encryption standards. As you can see, first of all, in the first step, in fact, the only transformation is adding the round key to our plain text here. Here we have our first key, which will be XOR with our plain text. After that, as you can see, the first round number 1, will be started, consisting of 4 transformation phases. The first is substitution, then we will have shift row, and then the next step is mix column, and finally add round key is the final phase of this round. As you can see, the only step that involve the subkey is add round key. In this step only we use our subkey, but for the other steps we don't need any keys. They are keyless. Okay? This number of rounds are repeated till the round number 9. And finally, at the last round, as you can see here, we have only substitution, shift row, and add round key. And the step of mix column is discarded in the last round. This is in fact the construction of AES standards, and in reality we cannot discuss about that. Consider that for each round we have a sub key, consists of 4 words. For instance, here words 0 till 3, then words 4 till 7, and finally in the last step we have words 40 till 43. Because our keys are also considered like our state as a matrix. Okay, and similarly for decryption we repeat exactly the same rounds but in inverse order. As you can see here, for decryption, first of all we use or we implement add round key like the first one when we was encrypted, when our plain text was encrypted. Here, first of all, our ciphertext will be XOR with the round key, which is the last one. And then for the first round, as you can see, we do the same shift round and substitution and adding round key and also column mix. But all of these steps are implemented in inverse, because all of those steps that are implemented for encryption are reversible, which means that we can use them in inverse methods. And as you can see, maybe more clear in this slide, similarly for decryption, the last round only consists of 3 transformation. Okay, and in fact the inverse of mixed column transformation will not be included in the last part, like the last part of encryption. And this diagram clearly shows the main encryption rounds. Here you have your first state. In fact, you have an array consists of 4 words. Each cell in your matrix will be transformed and substituted by using a box, and will yield a new state again. After that, as you can see, you have shift row step, which some in fact rows are shifted, again outputting another new state, and then the state of mixed column will be implemented, and finally the round key will be XOR with our state, resulting the final state here. It is clear that for each round we have a round key. In fact, we need a new subkey for each round, which means that our keys are not applied many times. Okay, and before the first round, only the initial state that will be applied is adding the round key, as I explained in the previous slides. And in the last step, we don't have the step of mixed column. The important point here is that consider that each of those transformations separately, they don't provide security. Even though this step, which is depend on a secret key, cannot again provide enough security. In fact, we need to have all of these steps together and repeating them several times to have enough level or acceptable level of security. It is so important to know this maybe simple point, but very important point. Hence, we repeat all of these steps in several rounds to provide enough and acceptable level of security. Okay? Substitution. As I explained, first of all, we have substitution. As you know, substitution is implemented and is done using substitution boxes or S-box. As you maybe know, the input of this S-box is our state. Okay? Using this S-box, we can find which element will be replaced in our matrix. Okay? But how it works? You know that you can consider this part as index 1, 1. Okay? Each byte can be divided into 2 bits. In fact, the left sorry, let me draw, it will be easier. We can divide each byte mainly into 2 parts. Okay? The bits which are considered in the left part will show the number of rows in S-box, and the bits in our right side will show the number of column, and the intersection of this row and column will be the value that we will be replace it with our S11. Okay? Here you can see an example of S-box and also the inverse of our S-box. For an example, consider that we have bytes consisting 9, 5. Okay, which have been shown in binary, and then we can see them here. The first part, 9, shows the number of rows, and the second or right side shows the number of columns. The intersection of this row and column is this part, which is equal to value 2a. Okay? Hence, we replace this value 9, 5 with the value of 2a in hexadecimal. Similarly, for the inverse, in fact, when we try to decrypt our value, we do the same thing. We have the value of 2a. Hence, the left side shows the number of rows, and the right side, similarly, the number of columns. And similarly, the intersection is equal to value 9, 5. Okay? There are some discussion here about how we build this S-box and its inverse S-box, which is beyond of our discussion. The other transformation is shift row. In this transformation, in fact, we consider the first row to be the same, unchanged, as you can see here. For the second one, we shift one byte to the left, as you can see here. The second one is replaced at the first place here. Then the third one in the place of the second, and so and finally the first one is replaced in the last. For the third row, we considered 2 byte shifting. In fact, the third one is replaced with the first one, and so on. This is the stage of shifting rows. Okay, in fact, the reason for implementing shift rows is too confusing the attacker about our original plaintext, because our plaintext is organized in this matrix, which each column shows one part of plaintext, and when we mix them, in fact, we are confusing the attacker to know and infer about our plaintext or our original message. And finally, mixing the column is something like doing a multiplication. Each column of our state will be multiplied by a matrix, yielding a new state. In fact, this matrix, the coefficients of this matrix for encryption is considered very simple, and only they are doing some shifting or XORing. This is mainly because for the easy implementation. And for the inverse mixed column, the coefficients of this matrix is more complex to provide us more, in fact, security.